View speaker. Look at this and then. Yeah, 1 second. I think this is about the best I can do. Oh, no. Give me a second. Yeah.
Solid for you guys?
Yeah, whenever you're ready.
Fantastic. Okay, well, thanks for attending, folks. So, as I said, this talk, I gave a version of this last year at the Society of Physics Students meeting. And I spoke more about quantum computing than I'll probably speak over here, which is ironic considering that this is the Quantum Computing Club at Columbia. Regardless, we will talk about quantum computing and one of the most fundamental parts of it, entanglement. In particular, we're going to look at what are called Bell's inequalities. We're going to focus on one in particular, the CHSH inequality, and show why a hidden variable theory of quantum mechanics cannot be true if you look at Bell's argument. So, oops. Okay, a little bit about me. Past work, I did my undergrad in physics and math at Columbia, graduated last year, co-founded CUQCC with Akshat and Manny, and also co-taught one of the quantum computing courses at Columbia under Sebastian Will's guidance. My current work is I'm doing a master's at Cambridge, and I'm also an incoming PhD student at MIT. My research for the PhD so far does not involve quantum computing. It instead involves heavy ion collision theory, and I've been working with Krishna Rajagopal at MIT on that. Okay, so today we're going to be talking about entanglement in quantum computing. Here are the topics. So we're going to talk about entanglement in the EPR paradox. This basically set the scene for quantum mechanics as we know it today. We're going to talk about the two-photon entanglement experiment that will provide a counter-argument to the EPR paradox. In particular, we're going to violate something called the CHSH inequality. This might ring a bell because the Nobel Prize for Physics last year was awarded to 3 physicists whose experiments were about breaking or violating such inequalities to demonstrate entanglement. And then the third topic we're going to cover is quantum teleportation. It's an application of entanglement. Really what it is a data transfer protocol using quantum mechanics. Okay, if you guys have questions at any point, just stop me and ask. Okay.
Can you see it?
Sorry?
Yes, like the room?
Yes, I can. Cool. Okay, so let's talk about entanglement. The first thing when we talk about entanglement is quantum states. Before we can talk about entangling quantum states, we need to understand what they are. A 2-level quantum state is something that has 2 energy levels. It's a particle that occupies 2 energy levels. These can be dictated typically using spin. And we say that these energy levels are 0 or 1. This is analogous to bits in classical computers where we have 0 and 1 bits. Similarly, we have 0 and 1 quantum bits over here. The difference between classical bits and quantum bits, however, is the fact that the state of the bit in quantum mechanics can be written as a probability distribution. Essentially, these coefficients C0 and C1 out in front dictate the probability of measuring this bit to be in the 0 state or the 1 state. So the magnitude squared of C0 is the probability of finding this bit in the 0 state, and then the magnitude squared of C1 is the probability of finding this bit in the 1 state. Okay, so that's a single 2-level quantum state. A 2-qubit state, so if we have 2 of these qubits, or 2 quantum bits, we can write it down like this. So each quantum bit can take on energy values of 0 or 1. So we have one configuration where both of them are in the 0 state, another where the first is in the 0 state, second is in the 1 state, another where the first is in the 1 state and the second is in the 0 state, and then a configuration where both of them are in the 1 state. Again, we have coefficients out in front of these. We call them state vectors. We have coefficients out in front of these state vectors that determine the probability of finding the system in that configuration. Okay, so this is a 2-qubit quantum state. Okay, so a 2-qubit quantum state is entangled if it can't be separated into a product state of 2 qubits. Essentially, what I'm saying is take some state, and if you can't write it as the product of 2 independent state vectors for each qubit, then we say that this system is entangled. So in this case, if we have the state of finding both particles in either the 0 state or the 1 state with equal probability, no matter how hard you try, you won't be able to split this up into a product of 2 independent qubit states. By independent qubit states, I mean something that looks like this. You just won't be able to. So if you're unable to do this, we say that your 2-qubit state is entangled. Another way to think about this is if you were to measure one of the qubits in the 0 state, you would immediately know that the second qubit needs to be in the 0 state as well. Similarly, if you measure one of the qubits to be in the 1 state, you would immediately know that the other one is in the 1 state. Let's look at a cartoon to understand this without the equations. So let's prepare an entangled pair of particles. We have 2 particles here. They're just red and blue. And let's say that we can find them either in the up state or the down state. But if we find one of them in the up state, the other one has to also be in the up state. And if we find one of them in the down state, the other also has to be in the down state. Now let's separate them by a large distance, okay? Take one at the, so keep one here and then take the other one to the edge of the observable universe. Okay, now let's make a measurement on the one here. Let's suppose we find it to be in the up state. Can anyone tell me what state this should be in?
Go for it.
The up state?
The up state, correct. Yeah, because if we find this one in the up state, the only other possibility for finding the second particle is also in the up state. Now, here's the catch. We've separated it by a large distance. We made this measurement, found that the blue particle is in the up state, and then immediately knew that the red particle must also be in the up state. Now, if we were to say that measuring this particle to be in the up state caused the red one to be in the up state as well, then you have what Einstein called spooky action at a distance. It's a signal that travels faster than light, causing the state of the red particle to collapse onto an up state. But this would violate special relativity. That can't happen. Okay, so what's going on here? We call this the EPR paradox. It's named after Einstein, Podolsky, and Rosen. EPR argued that any measurement that is definitively predictable corresponds to a physical fact about the system, and that any complete theory of the underlying nature must include this fact in its mathematics. So, for example, measuring this, the spin of the blue particle to be up gave us definitive knowledge of the spin of the second particle. We knew that it also had to be up. And the other thing is we knew that this was immediate. We knew we had access to this information immediately upon the first measurement. Now, because special relativity doesn't allow us knowing about one of the spins to cause the other spin to change, that can't have happened. So none of the states were caused to be changed. Instead, a resolution is that the second particle, the red particle, must have been in the up state to begin with. So it must have been in that state, even if no measurement was made. Because if we had made a measurement, there's no way that the state would have had time to change. Okay, so it must have started in the upstate and must have been in there when we made our measurement. Now, this system doesn't allow for that. It says that it can be up or it can be down. So the system doesn't encapsulate the fact that it must have been up to begin with in it. So EPR said that there must be some element of physical reality, what we call a local hidden variable, that determines the measurement of particle 2. So there must be some hidden variable in our theory that we don't know about, we don't have access to, that determined the particle to be in the upstate to begin with. Now, since quantum mechanics, since that equation did not address this hidden variable, quantum mechanics must be an incomplete description of the underlying reality. So this was EPR's conclusion, that quantum mechanics is incomplete. Okay, does that make sense? Does that track to folks? Any questions? Awesome. Okay. So that was EPR's conclusion. And then comes along Bell. Now, John Bell in 1964 counters EPR's argument, among many others. But Bell says that if you do have a theory that has hidden variables to account for this incomplete description of quantum mechanics, then it would predict certain bounds on a quantity called a correlation. We're going to construct this quantity, but if these bounds were violated, then it would demonstrate that quantum mechanics doesn't obey such a local hidden variable theory. It means that that type of a hidden variable just does not exist in quantum mechanics. So let's take a closer look at what this means. So we have a hypothesis. Let's construct a theory of hidden variables. First, we assume that these hidden variables exist and that they determine the outcomes of any measurements carried out on our particles. The second hypothesis is that these hidden variables are independent. They arise with some probability and are independent of the measurements that are actually carried out. Basically, the hidden variables don't care about what axis we make our measurement along. Just as we could have measured the particles to be spin up or down, we could have switched axes and said, let's measure it to be either right or left. The hidden variables don't care which axis we use. Okay, so we have hidden variables. They're independent of the choice of axis of measurement. Simple enough. Okay. If we take these two hypotheses to be true, then we can define an object called the correlator, S, which is bounded. And in particular, it's bounded in the system that we'll talk about, it'll be bounded by this inequality, where the correlator is less than or equal to 2. This is a simpler, convenient version of Bell's original inequality. This is what we call the CHSH inequality. Or Clauser-Horn-Chimney-Holt inequality. Okay, so let's get into it. We can test this in an experiment. We call this the two-photon entanglement experiment. Basically, what we're doing is we're going to entangle two photons and then construct this correlator S and see whether or not it gives us values that are always less than 2. The experiments that violated Bell's inequalities won the Nobel Prize in 2022. And here's the best part. You can actually do these experiments at Columbia. So this is a photo of me and my friend Ashwath, where we were trying to get this apparatus to work. We were lucky enough to actually conduct this experiment as the 2022 Nobel Prize was being announced. Okay. So let's get into the experiment. Here's the setup. We use something called QTools, where we basically have a laser, a beam of photons that goes through a lens, focuses it, and bounces it off some mirrors. Now, this beam of photons has horizontally polarized light and vertically polarized light. You can think of these as the 0 and the 1 states we've been talking about, or up and down, however you want to think about it. Basically, it's a two-level system with one of the levels being horizontal polarization and the other level being vertical polarization. We send it through what are called spontaneous parametric down conversion crystals. These crystals take a horizontally polarized photon and splits it into two vertically polarized photons. Similarly, it takes a vertically polarized photon and splits that into two horizontally polarized photons. Now, once that happens, we notice that we've been sending in a randomly polarized beam of light. It has equal parts of horizontally polarized photons and vertically polarized photons. So if we were to send it through these spontaneous parametric down conversion crystals, these photons would turn into V and V, and then these photons would turn into H and H. Now, this is an entangled state. We see that if we measure one of the photons to be vertically polarized, the other one must also be, and if we measure one to be horizontally polarized, the other one must also be horizontally polarized. Okay, so this is the setup of the experiment. It's how we create entangled pairs of photons. Now, what about the correlator? So in order to construct this correlator, we need to make measurements. So we have to measure the photon's polarization in different bases. So bases that are rotated from the horizontal and vertical bases. We just call these rotated bases plus and minus, and they're rotated using some angle alpha or beta in this case. So we first construct a probability of measuring the polarization in this plus or minus basis with different angles for rotating our axes. That's given by this state here. Don't worry too much if the mathematics here doesn't track. The punchline doesn't require this mathematics. It's just there so that if you wanted to derive it yourself, you could. So we make measurements in different bases. We have a probability of finding these photons in the plus or the minus state in these rotated bases. And we can use these probabilities to define a correlation. We call it E as such, where we just add polarizations and add probabilities and subtract them for each of these plus or minus polarization states. It turns out that if you were to write down the math here, you would get a cosine function that depends on the difference between the rotations of your axes. And then you can use this correlation to define a second measure of correlation. We call this S, and the second measure depends on 4 different angles. So you measure your 2 photons using 2 polarizers that have been rotated at some specified angles, and then you do this again for another pair of photons at different angles. So in this way, if you were to add up the first correlation, add or subtract, depending on the scheme here, you get an addition or subtraction of different cosine functions. And eventually, you can show that all of this must be less than 2, regardless of what alpha, alpha prime, beta, beta prime angles you've chosen. Okay, so if we have a theory of quantum mechanics that includes the system of hidden variables we hypothesized, then this correlator must be bounded as such. This is what's called the CHSH inequality. If we measure correlations larger than 2 in our experiment, then this inequality is violated, and entanglement can't be described using this particular hidden variable theory. I say this particular hidden variable theory because it doesn't account for every possible configuration of hidden variables. There are other types of hidden variable theories that we won't get into, but this one's a fairly broad one to rule out if we're able. Okay, any questions? Cool.
We're good here,
Oh.
yeah.
Okay, awesome. So let's look at the results. Ashwath and I carried out this experiment last year, and this is what we got. We set our polarizers at certain angles. I think it was something like 45 degrees alpha and beta, and then negative 45 alpha prime, beta prime, or some configuration like that. And we just measured values of S for different lengths of time that we were sending photons in. The integration time here, the x-axis here on this plot, is just the length of time over which we were sending in photons and carrying out measurements. And we noticed that for entangled photons, so when we did do spontaneous parametric down conversion, we got values of S that were consistently greater than 2 for all integration times. And then when we sent in non-entangled photons, you can think of this as a control in the measurement, we got values of S that were less than 2 for all integration times. This is very good because if we got values of S greater than 2 when we were sending in non-entangled photons, that wouldn't make sense because you should only be getting S greater than 2 if they're entangled. Okay, so what does this mean? First off, entangled photons displayed values of S over 2 consistently for a specific rotation of the polarizers. There were rotations of polarizers that would give us S less than 2, but once you have an S value greater than 2, you've already broken the CHSH inequality. The second thing is unentangled photons displayed values of S less than 2 for all rotations of the polarizers. This is important because we don't want unentangled photons giving us a correlator value greater than 2. And then the third point is that there were errors in our calculation of S. This is just because we had background noise from the environment and the lasers were slightly misaligned. But as you can see, the error bars are all greater than 2. So we don't need to worry about whether or not this measurement was less than, measurement of S was less than 2. Okay, so the conclusion is quantum mechanics is not described by such a local hidden variable theory because we violated the CHSH inequality. Okay, this is pretty big. This says that EPR, at least the version of the local hidden variable theory that we hypothesized, is incorrect. So quantum mechanics is a non-local theory of nature. It's not one that violates special relativity, as we'll see with an application of it. So it must still obey special relativity because making measurements on entangled pairs of particles doesn't cause any of the particles to collapse onto a particular state. Okay, the point is local hidden variables in this case are not a thing. Okay, now there's an unproven claim here, and that claim is much stronger. It says quantum mechanics is not described by any local hidden variable theory. So there could be hypotheses that differ from ours, local hidden variable theories that are different from the ones we hypothesized, that this inequality doesn't take into account. So I'm not stating that quantum mechanics is not described by any local hidden variable theory. It's just not described by this very broad one. Okay, questions here?
1 second. Okay.
Alignment. Sorry for the errors that because I don't know
Oh, sure.
few tools.
Yeah.
Like it's one of those things that's like if you are doing this experiment again, is there like a procedure with the laser alignment that like reduces the error in the process? Okay.
Yeah, so there is. In fact, the value, so the maximum value and the value we should have gotten for S is about 2 times the square root of 2, which is not what we got. We got something that was much lower. Now, if I recall correctly, groups that did this experiment after us were able to fix the alignment issues. And I think, so we did our experiment in fall 2022. And then in spring 2023, the last group to conduct this experiment got much better results. I think they had correlation values greater than 2.5. Of course, I don't have access to that data. But yeah, you can fix the alignment issues. And in fact, groups did fix the alignment issues.
For background noise, that sounds like trickier. I mean,
yeah,
do you like put it inside a Faraday cage or like a lead box or something, or
yeah, so I think the best way to show this is using this picture here. So as you can see, this apparatus is covered on all sides with this black frame. It's basically to shield it from any photons from the environment, like light in the room or light from the window. The window had no blinds, so light would inevitably get in. And then we also had a cover, which is not shown here, but another black frame that we just put on top of this so that we can control any stray photons going in to the apparatus. It wasn't perfect, and whenever we ran this experiment, we had to turn the lights off. But that's not the biggest contribution to the errors we're seeing. The biggest contribution came from misalignment of this apparatus. It was actually quite hard. Most of the time we spent was on aligning all the mirrors, aligning the polarizers, aligning the beam. So that took quite a while, and it was an iterative process. So it's a good thing that groups after us were able to improve upon our measurement. So even though ours was above 2, it was nowhere close to what the expected value or what the theoretically predicted value is, which is 2 times the square root of 2.
Is that the Terrellson, or how do you pronounce the name? Terrellson's bound for quality, the 2 times the square root of 2, or I assume that that's like the actual target, like, and we can get close, but it's difficult to. Is that the bound that you're talking about?
I'm not sure what name it's given, but yes. So instead of seeing the magnitude of the correlator here to be less than 2, in a theory of quantum mechanics without hidden variables, this bound should be 2 times the square root of 2. And the setup of the polarizers that we used in our experiment should have given us that value. It should have been the maximal correlator. There are configurations of the polarizers that would give us something less than the maximal value. But as long as it's greater than 2, we can rule out this hidden variable theory.
Can you go to the plots you showed earlier?
Yeah.
So you have this wave plate. What exactly does the wave plate do here? Because that clearly is the distinguishing factor between the two plots here.
The wave plate is the parametric down conversion crystal.
Okay.
Yeah.
Cool.
So that's the thing that actually splits. Oops. That actually splits the photons like this. So if we were to remove the wave plate, this is the state we start with, which is not entangled at all.
Okay. Which class is this for? Is it like intermediate physics lab?
Yeah, so this is intermediate physics lab.
Okay. That's cool.
Yeah.
Perfect. I think what does that mean to split a photon into like entangled photons?
That is a good question. My guess is that it has to do with some kind of scattering that happens within the crystal. And as a result of that scattering, you just get 2 photons from one. So then one just decays into 2.
So this magical crystal just creating entangled pairs like all the time?
Yeah.
How do we know that? Just curious.
We know that because of this measurement, in fact. So this is not just a proof of the CHSH inequality being violated. It's also a proof of entanglement, because you can only get values of S greater than 2 if you have entanglement. Without entanglement, you won't be able to get that. So like you'll get what you see on the right here. That's
Okay.
how we know. Yeah.
This is experimentally showing that entanglement is what occurs, not local hidden variables.
Correct. Exactly.
Gotcha. Wonderful.
Yeah.
We're good.
Awesome. Cool. How do we do this on a computer? How can we do this from like your living room, right? Or your dorm room? The way we do it is using quantum circuits. So you can implement entanglement and any quantum operation, for that matter, on a quantum circuit. An example of quantum circuits are the ones that are built using IBM's Qiskit. So you can encode a quantum circuit onto IBM's cloud computing platform for quantum computing. And they base their circuits on superconducting qubits. These are also called transmons. Now, just like you have energy splitting in the harmonic oscillator, you can have energy splitting in what's called an anharmonic oscillator. In the harmonic oscillator, the distance between energy levels is constant. But with a transmon, with an anharmonic oscillator, these differences between energy levels are non-uniform. So the difference between the 0th and the first energy level is larger than the difference between the first and the second. This way you can isolate energy levels. You can tell whether a particle is in the 0 state or the 1 state, depending on the difference between their energies. And similarly, you can tell if it's in this 2 state if it has an energy difference that's lower. Okay, so superconducting qubits called transmons use anharmonic oscillators. This is an example of a physical implementation of a quantum bit. And we build circuits just like classical circuits in computers today. So an example of a gate operation in a circuit is a NOT gate. So classically, it takes in a 0 and then it outputs a 1. You can do the same with quantum mechanics, where you take in a 0 state and then output a 1 state, or you take in a 1 state and output a 0 state. This is what the gate matrix looks like for this. And we notice that this matrix 0, 1, 1, 0, where basically you have inputs in this column and then outputs in this column, is the same thing as the Pauli X matrix. So we call this an X gate. So a NOT gate classically is equivalent to an X gate, an X quantum gate, or the Pauli X matrix. Now, there are also gate operations for each of the Pauli matrices, the Y and the Z Pauli matrices, as well as the identity. The identity does nothing. So we can represent quantum gate operations as matrices, where basically you feed in some state written as a vector. I should have put that on this slide, but you just feed in quantum states written as column vectors with coefficients C0 and C1 and act on them with matrices like such. So you can act on them with X, Y, Z, or I gates. But you can also act on them with more complicated gates. Let's say you wanted to rotate a quantum state. So if you wanted to rotate the 0 state onto something we call the plus state, which is basically an equal combination of 0 and 1 with a plus phase, you can do this operation. And let's say you wanted to rotate the 1 state to another equal combination of 0 and 1 states, but with a minus phase. Well, if you were to write down the gate matrix for this, it looks like such. We call this the Hadamard gate. Turns out to be really important during entanglement, especially because, as you can see, we're creating an equal amount of 0 and 1 states just like we started with an equal amount of 0 and 1 of horizontal and vertical photons in our experiment. But we'll get back to this. A second gate that's relevant to entanglement is something called the C0 gate, or control knot. Its matrix looks like this. The way to understand this is it acts on 2 qubits. These qubits can be in the 0 or 1 state each. So let's take a look at what these qubits are before we act on them with a C0 gate. So we have 1 qubit that's the control, and then the second that's the target. If the target state differs from the control state, we send the target state to 1, and if it's the same as the control state, we send it to 0. So in this case, the target state is the same as the control state. The control always stays the same, and we send the target state to 0. Over here, the target state is different from the control state, so we send it to 1. Over here, the target state is again different from the control state, so we send the target state to 1, keep the control. And then over here, both of them are the same, so we send the target state to 0 and keep the control. This is what the matrix looks like, and you can write it down mathematically using modular arithmetic as such. Pictorially, on a circuit, this is how we denote the Hadamard gate, just as an H. And then this is how we denote the C0 gate, where this represents the control. It is basically the identity operator. And then this represents this addition mod 2, this modular arithmetic operator. Okay, questions on these gates?
All right, go for it.
On like a physical level, do you know what it
Yeah.
means to apply a gate to a qubit? Like, is there any intuitive way to understand that?
On a physical level. So the way to, do I have an image? I don't. Okay. So the way to understand this is really as rotations on what's called the Bloch sphere. Have you heard of that before?
No.
Okay. Oops. Let me see if I have. Yeah, okay. So this
No.
sphere here. So this is something we call the Bloch sphere. It represents the state space of a single qubit. Typically, by convention, we choose this point at the top of the sphere to represent the 0 state, and then this point at the bottom of the sphere to represent the 1 state. And combinations of these 0 and 1 states occur at different points on this sphere. So, for example, I think if you were to act with an X gate on this, it flips this arrow down so that the 0 points towards the 1, or if it started in the 1, it flips it back up to the 0 state. A Hadamard similarly does some rotations. So it rotates this vector and sends it to the state that lies at 0 plus 1, which I think is over here or over here. It's one of those two. I'm not sure. But all quantum gate operations on single qubits are rotations on the Bloch sphere. Now, you can also think about operations on 2 qubits as rotations on some higher dimensional sphere. Now, the reason why I say higher dimensional is precisely because of entanglement. Let's say you wanted to represent 2 qubits just on 2 independent spheres. Well, if you were to do that, you have an issue. You can never write down an entangled state using this 2-sphere representation. Because if you can draw the state of an entangled pair of qubits using 2 independent spheres, you basically have 2 independent states. So the state isn't entangled at all. Okay, so you can't use 2 independent spheres to write down or to represent a 2-qubit state. You instead need to talk about spheres of higher dimension. So I think that's the best way to think about what's what's happening here.
So just to add, like if you're talking about like the gate, like the physical gates themselves, like in context, I think like the answers that any of us here at this table will give is going to be from a theoretical perspective. And the real answer is a little unsatisfying. Like in terms of like what is it physically depends on the implementation, and there's dozens of like different, like some of them use like ion entanglement and some of them use like superconducting.
Yeah.
It depends on like which you're done about how they do it, and I don't know anything about it. I'm guessing some of us here.
No, I think most of us come from a theoretical background.
Yeah.
Other things.
Yeah.
I want
It's probably the best.
Yeah. We can do block spheres. I got a question for you, Arjun.
Sure.
You talk about transmon. What exactly is a transmon? Like physically, what does it mean? Which again may result in something else.
That is a good question.
Yeah.
Physically, what is it?
I wonder if it's like some particle or something, like I don't know, some polarized, I don't know, like alpha particle. I don't know. I wonder. Because I imagine if it's something that you have multiple energy levels for, but it's decreasing, it's some sort of like electron-based particle,
Yeah.
I'd imagine. But yeah, I don't know. Its wave also looks weird too. Like it goes off and then it's decreasing after a while. And I imagine, is it like a thing where with the electron, if there's like a free energy where you add a certain amount of energy, you free the particle? But does it make sense?
Yeah. So I think you can think about it as this like, okay, I'm not exactly sure what a transmon is, but intuitively, when I think of something that has energy levels that are not the same, or like differences in energy levels that are not the same across all energy levels, I would think about something like an atom, right? It has different orbitals, and the differences between the energy of each of these orbitals is different. That's what I'm thinking of, although that is not a transmon. But that's a type of system that allows you to like write down a 0 state or a 1 state definitively without having to guess. Exactly what a transmon is, actually don't know.
That's fair. That's
Yeah.
fair. We're all theory people, I guess.
Yeah.
Yeah, that's fair. Yeah. Another question? Good. I think we're good right now.
Okay, cool. Oh, and yeah, just by the way, all these questions, whenever I say I don't know, I'll spend some time and figure out the answer to it, and then I'll post it on the web page for the talk. Stay
That'd be
tuned for
lovely.
that. Yeah.
Perfect. You'll send it if you send the thing to me, I can put it in the you have it actually. You post it to your
Cool.
website. Yeah.
Sounds good. Awesome. So let's build this entanglement circuit. How am I doing? Oh, okay. I don't have much time, but that's fine. So let's build this entanglement circuit. We start with 2 qubits, both in the 0 state. Okay, let's start with both of them in the 0 state. And we hit it with the Hadamard first, and then the C0 gate. Now, if we were to hit it with the Hadamard first, this is the 0th qubit, and this is the first. So we hit the 0th qubit with the Hadamard, it turns it into a plus state. Now we can write down this plus state basically as the product between the plus state and the 0 state. So it's the product between 0 plus 1 and then 0. So we just slip the 0 onto each of these. And now we perform a C0 operation on these 2 qubits. So we perform the C0 operation linearly on this state and then this state. And if we were to do that, then we notice that these two this is the control, this is the target. Both of them have the same value. So it does nothing to it. The target state remains 0. But a C0 acting on this would change the target qubit to a 1 because the target and the control differ. So we get 0, 0 plus 1, 1. And then we have this normalization factor out here from the Hadamard. This is one of the Bell states. This is an entangled pair of qubits. So this simple set of 2 quantum gate operations gives us an entangled pair of qubits. Fair enough. Okay, let's talk about an application of entanglement in quantum circuits. In particular, we're going to talk about quantum teleportation. And we're going to do it without any equations. Typically, the way this is taught is with equations. It's easy to track the mathematics if you know what's happening. But at the same time, it's just as instructive to understand what's actually going on at an information level without any of the equations. So here's a crash course in teleportation. So teleportation is really information transfer. We're not going to be taking one particle and then cloning it in a different location. We're going to be taking the information that one particle contains and transporting it onto a second particle. Now, like I said, we're not cloning anything. So once we transfer that information, it's lost from the original particle. Let's see how we do this. So we start off with two individuals, Alice and Bob. They each share an entangled photon and also a classical channel of communication. Like they just have cell phones. This will be necessary, as we'll see. Okay, again, two individuals. We need an entangled pair of photons for this to work. We're going to be using quantum mechanics and entanglement, and then a classical communication channel. Okay, now let's say Alice wants to send a red state over to Bob using an entangled pair of photons. She starts with some quantum state, a red state. She doesn't know what it is. She doesn't have to know what it is, but it's been prepared. And we also have an entangled pair of qubits that are shared between Alice and Bob. Alice takes one of them, Bob takes the other. Now, Alice entangles her qubit with one of the entangled ones and transfers some of that quantum information to Bob via entanglement. How did this happen? So I'll go back one slide. Once Alice entangled her red state with the blue particle, one of the entangled particles, some of that information was transferred onto it. But we know that this blue particle was entangled with the one that Bob has. So that red information is also imparted onto Bob's blue qubit. Okay, so now we have a bunch of information being shared across 3 qubits. How do we get this to be entirely red, entirely what Alice's original state was? Well, Alice has to take a measurement. She needs to take a measurement and measure whether her 2 qubits were in the 0 or the 1 state each. She makes this measurement and tells Bob about it. She relays that information to Bob. And once that's done, well, she has to use a classical communication channel to do this. Once that's done, Bob can then apply a series of conditional gate operations, either X gates or Z gates, onto his qubit, depending on the measurement that he got from Alice. And once he applies those gate operations, he immediately recovers Alice's original state. Okay, so what just happened here? 1, Alice transferred the quantum information in her qubit to Bob. Neither of them needed to know what the original state was. And the information about these states was never known by any party. That's important. Knowledge of the information doesn't matter here. It can be kept secret from any person involved. Now, another big piece of information is that classical information transfer was necessary. If we didn't have that classical communication channel between Alice and Bob, then this data transfer protocol would violate special relativity, because we're sending information from one individual to another, separated at some distance. And if we didn't use classical communication channels, that data transfer would happen instantaneously, and it would violate special relativity. Quantum mechanics has to be compatible with it, so this can't happen. So classical information transfer was necessary. And then the final thing that happened was that Alice's original state was completely transferred. If you notice, she took measurements. Once she made measurements on her qubits, it lost all the probabilistic information it contained, and now they both just act as classical bits. So she has lost her original state, and Bob has it now. So we've not cloned Alice's state, we've simply transferred it to Bob's qubit. Okay, that's it. That's quantum teleportation. It's just that simple. You don't need math to understand it. You don't need to go through the equations. All it takes is an understanding of information and entanglement. It's that simple. Any questions about that?
I think we're good on our end. Don't think we have any questions. If anyone on Zoom has any questions, ask it. No? Okay. Yeah, because there's also like segues between this and then obviously you can't clone with quantum information too.
Mhm.
That's a whole, you can also discuss that as a whole too. Also make this too long.
Yeah.
I think.
Yeah.
Yeah.
The whole thing about this state not being cloned has to do with something called the no cloning theorem. There's a theorem in quantum mechanics that says that you can't clone a state. So if you were to create a quantum state, you can't make another copy of it using that state. Now, you can create another state that is the same using the same process, but you can't take one, do some operations on it to create another that looks exactly like it. So that's what no cloning means.
Yep.
You can also build a circuit that does all of this, where you prepare a state that Alice has, prepare an entangled pair of particles, entangle Alice's qubit with one of them, have Alice make those measurements, and then have Bob apply some conditional gate operations depending on the measurements he gets from Alice onto his qubit. And then he can check whether he has Alice's state using measurements of his own. So you can also build the circuit without knowing much of the math. Now, if you want to, yeah.
One question. If you go back, right, you can also
Yeah.
do this with less classical registers too, I'm pretty sure. Like
I don't know that.
You can only use you can use one, just CRZ, because you can
Okay.
feed the X and you apply the X, and then you do the same thing with the Z as well. Because you've already measured Z, so then you read that in, and then from the same register, since you already used X, then you can
Right.
apply it.
Yeah,
Just like, because you don't need to keep the information. But if you
that's a
want
good
to know
point.
the bit and faceless information, I guess it tells you what happened from the measurement itself. It's a good learning to check it, I guess.
Yeah, for sure.
Mhm. Yeah, this is great.
Awesome. And then
Yep.
just last slide, if you guys want, you can run this code yourself. All you need to do is install Qiskit, or just create an account on their online cloud computing platform, which is what I do. I don't use it locally. I just have an account over there, and you can get the code from my website to run it yourself. That's it. Thanks so much. If you have questions, now's the time.
All right. Questions overall, I think I'm good with questions. That's good. All right, I think we're good.
Thank you, Aaron.
Thank you.
Awesome. Thanks so much for having me. It was super fun to present.
Yeah, for sure. You can send me the website, or so you have, since you're in the Slack, you can post it to the social channel, and that's
Yeah.
where all the information will be about slides, websites, links, fun stuff. So yeah,
Sounds good.
thanks once
I
again.
will. Yep. Thanks, Akshat. Thanks, everyone.
Yeah. Yep. See you.
Have a great day. Bye.
You too. Have a good night.
Good night.